give it another. So it's a pleasure to have Professor John Bock, who will be telling us about microstructures arising from solid phase transformations. Over to you.
Thank you very much for the invitation, and it's been very nice visiting the Institute these last 3 weeks. I'm off the day after tomorrow. So I'm going to repeat that my visit here has been sponsored by the Royal Society through this use of Hamid Fellowship. Is that not working? I wonder. Completely frozen. It's completely frozen.
Oh, 1 minute. The mouse is moving, so
Yeah, I can't get it. Let's do exactly that. That's right. Let's close it. It's not shut.
okay, that will
Sure.
that will be the best idea. Actually, the screen
Let's do this one. See whether this works now. No. I need to kill the slideshow. Stop share. To kill the slideshow. Right. We're back to Zoom now. It's when you turn the recording on and off. Yes, what is it? Oh. Okay, sorry about that. Okay, so this talk is going to start what are called Martensitic Transformations. They involve so all alloys, metals, as you know, form from crystals. So there's an underlying crystal lattice, and Martensitic transformations involve a change of shape of that lattice as you pass through some critical temperature. So, for example, at a high temperature, you could be in the so-called austenite phase with a cubic lattice. So there's, there might be, say, an atom at each corner of a cubit in the middle. And we have a cubic structure, and then you reduce the temperature through critical temperature, and because of interactions between the atoms and how it depends on temperature, it wants to change shape. So in this case, from a cube to a tetragon. And it happens suddenly, like this. And because the original lattice has cubic symmetry, it's just as likely to stretch into a tetragon in this direction as it is in the other two cubic directions. And it may happen that in a material, when you reduce the temperature, in some places it's going to stretch in one direction, and in other places it's going to stretch in another direction. And all these things have got to fit together geometrically, and we'll see the sort of result of that. Okay. So now, in the cubic to orthorhombic transformation, say, for example, copper, aluminum, nickel, the change of shape is slightly different. You first of all, you stretch in one of the cubic directions, and then you stretch by different amounts in two face diagonal directions. So in the cubic tetragonal case, you have three tetragonal so-called variants of the low temperature phase, which is called Martensite. And in the cubic orthorhombic, you have six orthorhombic variants of the Martensite. And for other transformations, you can have 24 variants or 12 variants. Okay, so here's a picture. It's a high resolution electron micrograph, which shows you exactly what is happening in a cubic tetragonal transformation. So you see that this is after you've reduced the temperature below theta critical, and each dot represents an atom. It's a column of atoms perpendicular to the screen. This is in nickel manganese, which undergoes a cubic tetragonal transformation. You see the scale is 2 nanometers. And you see these interfaces. If you look very carefully at the dots, you see that on one side, so the cubic axes are like this and into the perpendicular to the screen. So you see that on one side, it's formed one tetragonal variant by stretching in this direction more. And on the other side, it's stretched in a different direction. It's chosen another variant. And they've got to fit together geometrically, and that's what these interfaces are. So why are there so many of these interfaces? Because this is, these are just, these bands alternate between 10 and 6 atomic spacings thick. So why is that incredibly fine microstructure formed? We'll see a bit about that later. Okay, so now how are we going to model this situation? So first of all, we're going to take the case of a single crystal. So the lattice, the original cubic lattice is the set, if you will. So in a polycrystal, there may be other regions where the lattice is turned in a different sort of grain of the polycrystal. First of all, we consider a single crystal. So we're going to consider a map Y from the reference configuration omega to R3, and the total free energy at a temperature theta. So we have to choose a reference configuration. So we'll choose it to be the austenite at the critical temperature. And so the free energy at temperature theta is going to be the integral of some density of C of the gradient of y at x, which you can identify with a 3×3 matrix, and the temperature. And the density, therefore, is defined for A in GL plus 3, which is the set of invertible matrices with positive determinant. And positive determinant because we don't want the deformed configuration to be reflected with respect to the underformed configuration. In fact, we actually want that this map is invertible, but that introduces global issues that I'm not going to talk about in this lecture. So the change of shape of the crystal lattice is given to you by a positive definite symmetric gradient, which we'll call U of theta. That's positive definite symmetric matrix. So now we're going to suppose that there's a sort of energy well structure. So we're going to look at the set K of theta, which is the set of matrices A with positive determinant that minimize the integrand. Okay, and we're going to suppose, we can suppose just by adding on some function of theta that C of A theta is 0 for every A in this set. So C is going to be non-negative, it's going to be 0 in this set. And let's suppose now that the temperature is less than the critical temperature. So now the K of theta, we assume, is going to be the union of a finite number m of energy wells. So here's the transformation strain. Well, U of theta was the transformation strain. Here we've got Ui of theta. So they're the distinct matrices Q, U theta, Q transpose, where Q belongs to the so-called point group of the austenite. So that's the point group is the rotations that map the austenite lattice to itself. And of course, if this was the cubic group, which is what we would usually have, that consists of 24 matrices. So you might think there'll be 24 of these matrices as Q runs through the A, but in fact, a lot of them will be the same. Some of them will be the same. And so we end up with M distinct such UIs. Now the SO3 at the front is because we want the energy to be rotationally invariant. If I take a material and I just do a rigid rotation, then that's not going to change the energy. So we see that this energy, the zero set of C is quite a complicated thing. It's a bunch of a finite number of copies of SO3 with these matrices UI of theta.
Sorry,
Yeah.
So when you said the austenite was the cubical lattice?
Usually we take the austenite to the cubic list, but it's not always, but usually we do.
And so do we have some information about what the function phi looks like?
The psi looks like, well, I'm talking more about it, but in principle, you could try and do some kind of first principles calculations from sort of atomistic models and so on. It turns out we're not going to need much information other than really what the set K of theta is. I mean, it depends what situations you're working on. If you can get by with just knowing what K of theta is.
I see. So what we're looking at is information about this this set K of theta, which is transformations which minimize the energy at a particular temperature.
They're the linear transformation to minimize the potential energy at that temperature. That's right. So, for example, if we take cubic to tetragonal, again we'll take PA to be the cubic group, and then you find that you calculate those matrices Q, U, as you say, U to be diagonal eta 2, eta 1, eta 1. So tetragon is a brick-like object with two sides equal to eta 1 and one side different, eta 2. And we suppose that eta 1 is not equal to eta 2. And it turns out that there's just three distinct matrices of the form Q, U, Q transpose as Q runs through the group. And they're what you expect them to be. You just use you put the eta 2 in the 2 and the 3 slot. Okay. And now cubic to orthorhombic, so for example, copper, aluminum, nickel. So remember that was the change of shape. So here is the U of theta. So there are three parameters now, alpha, beta, and gamma, that will depend on the temperature. So the beta, that's the stretching in the vertical direction, and these are the stretchings in the diagonal directions, and you work out, and there are six of them in this case, six distinct matrices, and there they all are. Not important for. Now, we saw in that high resolution picture interfaces. So this is a very important instrument.
Why do you expect different extractions? Is it because of
the interactions between the atoms? I mean, these are alloys that have different atoms, so different lattice sites and so on. Okay, so this is an important but fundamental calculation. Let's suppose that you have a piecewise affine map, a continuous piecewise affine map. And its gradient then, dy, so it's matrix, of course, it jumps across the plane x dot n is equal to k. So above the plane, it's equal to some value a, and below the plane, it's equal to some value b. And the question is, how are a and b related? And this is the answer, that a minus b is a vector tensor productive with the normal. And that's the so-called Hadamard jump condition. Of course, you can. This little a is you just act both sides on capital N, and you get little a is a minus b acting on the vector n. So that's absolutely critical calculation. Just which you do by equating tangential derivatives on either side of the interface, applying continuity. Okay, now we saw that there were distinct energy wells, and they were all of the form SO3 times some U. Okay, so now we would like to know whether we can make a zero energy interface. So that will correspond with a okay. So let's go back 1 second. Okay, so this of course is provided A is not equal to B. This is a rank 1 matrix. It's a tensor product of two vectors. It's a rank 1 matrix. Okay. So now the energy is minimized on these copies of SO3. And interfaces correspond to rank 1 connections between matrices. So we want to know when we can find a matrix on one SO3 times something and another matrix on SO3 times something else, which differ by a matrix of rank 1. Because if you can do that, that means you can find an interface between the gradients on each well. So here's a theorem which tells you when SO3 and SO3U, V are rank 1 connected, where U and V are positive definite symmetric matrices. And the answer is that U squared minus V squared is a non-zero constant times n tensor n tilde plus n tilde tensor n, the unit vectors n and n tilde. And if n tilde is not parallel to n, then there are exactly 2 rank 1 connections with any point on one of the wells and the other well. So if I take the point to be V, for example, there's exactly 2 points RU and R tilde U, which are rank 1 connected to V. Okay. And what's interesting is that the N and the N tilde, the normals corresponding to these rank 1 connections, are exactly the N and the N tilde that appear in this relation. So the 3 by 3 matrices, but if you, not knowing anything about this, you started doing it yourself, I promise you, you would cover pages and pages before realizing what the tricks are to do it right. So they're not completely trivial. Okay, corollary. Suppose you take 2 matrices in the same energy well. Okay, then this theorem tells you that U must equal, so in this case, U is equal to V, but the C has got to be non-zero. Okay, so impossible. So there's no rank 1 connections between matrices in the same energy well. Now, if Ui of theta and Uj are distinct Martensitic variants, then it turns out from the theorem that the 2 energy wells are rank 1 connected if and only if the determinant of Ui squared minus Uj squared is 0. That's because it has to be the form here tells you that it's something that has determinant 0, but the trace, in the case of Martensitic variance, the trace of the U squared is equal to the trace of the V squared. So I mean, once you know the determinant of this is 0, you can check that this holds. So, and the possible normals are orthogonal. That's because you take the trace of that matrix, which is 0, and you get twice C times n dot n tilde, which has to be 0. And the variants separated by such interfaces are typically called twins. Now, here's a very interesting remark. So suppose we take A in SO3. So that corresponds to the high temperature phase. Remember, we took the reference configuration to be the high temperature phase at the critical temperature, which corresponds to Y is equal to X, and the gradient of Y being the identity. So the energy well corresponding to the high temperature phase is SO3. SO3 times the identity. And now, could you make a rank 1 connection between the high temperature phase and one of the Martensitic variants? And this tells you, and the theorem tells you that that can only happen if Ui of C has middle eigenvalue 1. So I think that's more or less obvious. I mean, so now you've got one, so U is the identity now. Okay, so this obviously has to have an eigenvalue 1 because this is right. So I mean, I take something perpendicular to n and to it. So and so it turns out to be the middle eigenvalue because of the trace condition. Yeah.
Are you trying to justify why in these microscopic images we see various vertical lines,
planes,
vertical planes, of course, in 3 dimension. So the fact that there's this connection implies that I have these different matrices acting on the cubical lattice, and they're connected by the same thing on these vertical planes.
It's leading to calculations of what interfaces are possible between different zones. So here we're talking about whether you can go from the high temperature phase to the low temperature phase by just simply having a planar interface. And that's only possible if Ui at the critical temperature has middle eigenvalue 1, which of course you would expect never to happen. I mean, when does anything have exactly an eigenvalue 1? I mean, so you would expect that not to happen. But that's very, very interesting. Okay, so here's a sort of mathematical picture. So I write SO3 times something as a circle, which of course is not what it looks like, but there we go. And so if you've got a rank 1 connection between, say, SO3UI and SO3UJ, so that means, so rank 1 connections are line directions in red, right? So here's a point on the on SO3UI, and this is the rank 1 direction, and so it meets this energy well somewhere. Of course, it doesn't cut it anywhere else, right? Because there are no rank 1 connections from one well to itself. And now if you look at the energy along that line, you see it's going to be 0 here and 0 here, and it's going to be positive elsewhere. So it's going to be a non-convex function of the direction along this line. So that means that this function of C cannot be rank 1 convex. It cannot be convex in the direction of matrices of rank 1. Now, there's a very important condition called quasi-convexity, which happens to imply rank 1 convexity. So this means that of C is not quasi-convex. And the definition of quasi-convexity is this. It's a little bit, it's a kind of Jensen's inequality for gradients. So the function f of the gradient is quasi-convex if when you minimize this subject to linear boundary data, ux equals ax, then u identically equal to ax is a minimizer of this problem. So now, quasi-convexity is the central convexity condition of the multidimensional calculus variation. It's essentially necessary and sufficient for existence of minimizers, and it's implicated in everything. But unfortunately, we don't know how to tell whether the function is quasi-convex or not. But quasi-convexity does imply rank 1 convexity, and so we suspect then that we expect the minimizers of our integral will not exist in general. And that's the case. And in general, the gradients dyj of a minimizing sequence yj of the, so we minimize the energy with respect to some boundary data, for example. And so typically what will happen is that we'll get minimizing sequences. They will not converge to minimizers because there isn't a minimizer. But instead they will generate an infinitely fine microstructure in the limit as j goes to infinity. And of course, here the microstructure is not infinitely fine, and that's because we've ignored terms in the energy due to interfaces where the atomic environment is slightly different from if you're in the middle of a band, for example. But what's interesting about this model is that the fact that the minimum is not attained, in some sense, explains mathematically why you see these incredibly fine microstructures in materials. Well, how can we describe them mathematically? Well, one way to do it is through so-called gradient Young measures. So suppose you've got a sequence of gradients dyj, and you fix, for the moment, you fix j, and you fix a point x, and you fix a very small radius delta around x. And now you imagine picking a point z at random, uniformly distributed across this ball from bx delta, and you look and see what the value of the gradient of yj is at that point z. And that way you get a probability distribution. So it's the measure of the set of points where this measure gives to a set E of matrices the measure of the set of points where the range of y, j, and z is in E divided by the measure of the ball, right? And that's a probability measure on matrices, which depends, of course, on x, j, and delta. Okay. So what we do is we first let j go to infinity. So that will smear out all these oscillations across the ball, hopefully. And then we localize it by letting the radius go to 0. Okay. And then we should get something, if we're lucky, that depends only on x. Okay. And that is the so-called gradient Young measure that's generated by dyj. So if you do this, then a subsequence, for a suitable subsequence, this double limit will exist. It's weak star convergence of probability measures. But anyway, double limit like this, you end up with a parameterized family of probability measures, they're parameterized by the point x. Each one is a probability measure on matrices, in our case, 3 by 3 matrices. And what it gives you is the asymptotic distribution of the values of this sequence when you're very close to a point x in the limit as j goes to infinity. So its center of mass, which is the integral of a d nu x of a, that is the weak limit of the macroscopic deformation. Well, it's the weak limit of dyj. So that's the limit in the sense of averages of dyj. And we interpret that as the macroscopic deformation gradient. So for example, in that high resolution picture, if I stand a long way away from it, I don't see all these oscillations. Instead, I see the weak limit. Okay, that's the macroscopic thing that I see. Okay, so now when a new phase is nucleated in such a transformation, it's got to fit geometrically onto the parent phase. Okay? And that's an important ingredient for determining the microstructure morphology. And it leads to metastability when the two phases are geometrically incompatible. So this is typically how the high temperature phase changes to the low temperature phase. We showed that he couldn't do it by having a simple interface where here was the identity and here was some element in SO3 UI, right? Because in general, there are no such rank 1 connections. So what it does instead is it makes a very fine laminate of two rank 1 related variants of Martensite, and that matches onto the austenite. Okay, so mathematically it's like this. So you imagine that we have the sequence dyj, it's a minimizing sequence for the energy. Over here is the identity, because it's the austenite, and here it alternates between two values a and b, which are on the Martensitic wells. So dyj is equal to, say, a in these layers, so thickness lambda over j, and b in other layers, which are thickness 1 minus lambda over j. And of course, they've got to match, there has to be some kind of boundary layer to match them onto the identity. Now, using the Young measure over here would be a direct match for the identity, because you have probability 1 of seeing the matrix, the identity, and probability 0 of seeing the other matrix. And over here, you'll have a probability in the limit as j goes to infinity, you'll have a probability lambda of seeing the matrix A and 1 minus lambda of seeing the matrix B, because these layers are of thickness lambda to 1 minus lambda in ratio. And so the Young measure is it's lambda direct mass of A plus 1 minus lambda direct mass of B in this region. And these, if you do these calculations, you give you land upon famous formulae of material science with the so-called crystallographic theory of Martensite. So if you know what the transformation strain is, you find everything. You find the normals, you find the angles between these planes and this plane, you find out what the volume fractions are, and so on. So it's a very successful theory. I should have said that this work is a lot of what I'm going to describe was this joint work with Dick James from the University of Minnesota. Now, why should we expect that you have a simple laminate rather than a double laminate, for example. So why doesn't it look like that with the austenite over here and a double laminate of martensite over here? Why not? That would be a sort of non-classical interface. So, and that would correspond to having the macroscopic deformation gradient, the identity over here. Over here, it would be a constant. We assume it's a constant. And the F would belong to the so-called quasi-convexification of the martensitic energy wells. So the quasi-convexification of a set is done using in the same way as a convexification of a set is done, except we use quasi-convexity instead of convexity. So there's the actual definition. It's the centers of masses of a homogeneous gradient Young measure whose has support in K. Homogeneous means it doesn't depend on X. So that's for a compact subset of matrices. And so F, of course, would have to be identity plus B tensor N in order to match onto the austenite. And if you wanted to do that with Young measures, then you would have nu sub X as a Dirac mass of the identity over here. And here it would be a nu which is supported in the energy wells. So if you like, over here, everywhere you're using a martensitic gradient, which has zero energy. But you're allowed to have sort of boundary layers, which, I mean, there would be boundary layers between these things and here, which would vanish in the limit as J goes to infinity. Okay. Unfortunately, this quasi-convexification is unknown unless you have two variants, which is one of the problems about this theory, and it's an interesting connection between fundamental problems of the calculus of variations and actually calculus, and in particular these experiments. Well, for a long time we didn't know whether such non-classical interfaces existed, but I was part of a European network, and there was this very brilliant Czech experimentalist, Hans Scheiner, and he devised an amazing way to produce them. So these are the pictures that he showed. So up here we have the austenite, and here we have a double laminate of the martensite. Here's an even better picture. So this is this non-classical interface, austenite down here, and a double laminate of martensite. And you can by varying the double laminate, the volume fraction of the double laminate, you can even make the surface curved. Okay, now I wanted to say something about incompatibility induced metastability. So absolutely critical in all this affair is how these different gradients fit together. Okay, so here's one. So this is a special case of some work I did with Dick James, designed to explain hysteresis in some experiments of True and James on copper, aluminum, nickel, or single crystals. And so there's the experiment. You took a single crystal and you pulled on it in two directions, in one direction by a force sigma 1 and another direction by a force sigma 2. And it turns out that if you model this, you can reduce the situation to the following much simpler situation. You have an energy integral of W of dy, and W has critical points at two matrices only, A and B. And the difference between the values, well, B has slightly less energy, and so the difference between WA and WB is small. So WA turns out to be of C of A minus T dot A, and T is a matrix which involves this sigma 1 and sigma 2. And so this, you lose rotational invariance. So that's why you can have here just single matrices that are minimizers rather than copies of SO3 that are minimizers. Okay, but now it turns out when you do the calculations that the rank of A minus B is strictly bigger than 1. Okay, so you can't make a rank 1 connection between A and B. So suppose you're sitting here at A in the higher of the two energy wells, and we'd like to reduce the energy by introducing some of B. But we can't make an interface between B and A because it's geometrically impossible, right? So the theorem is that under suitable growth conditions, y bar AX is a local minimizer of I in L1. In other words, you can't nucleate this new phase. So at least you have to do something dramatic. So that there's some epsilon such that if you're L1 close to y bar, then the energy is bigger than or equal to the energy at y bar. And the idea is that since A and B are incompatible, if you try to nucleate a region where dy of x is B or near B, then because they're not compatible, there has to be a transition layer. And the gain in energy in the transition layer can be more than the loss of energy in the nucleated phase. And so anyway, it's quite an interesting kind of result.
Can you go back to so I didn't understand the phenomena of hysteresis.
Okay, so I didn't explain the phenomenon of hysteresis. I suppose I didn't explain it. The phenomenon is that when you start in this experiment, you start in one variant of the Martensite, and then you pull on it, and then it there's a certain sort of force that you have to do in order for it to transform to another variant. And that's actually to get it out of this little energy well of this, okay? Now suppose you try and go back, okay? Then you'll have to pull harder in order to, there's a difference in the forces in different directions. That's the phenomenon of hysteresis. Okay, now I'm going to show you a very interesting movie. So before I show you the movie, this is going to be nucleation of austenite and martensite. And these are, again, by this amazing experimentalist from China. So here's a lump of copper, aluminum, nickel, single crystal, and it's been somehow, you have to do this carefully, but this is a single crystal of martensite. So in other words, it has a constant gradient sitting in one of these martensitic energy wells. Okay? And this object here is the tip of a soldering iron. So this is, to start with, below the transformation temperature, where it wants to be in this martensitic phase. So now you heat it up with this soldering iron. Of course, now the temperature here is going to be way above theta critical. So you would expect the high temperature phase to be nucleated under the tip of the soldering iron, right? But that doesn't happen. It nucleates here at a corner. Okay? And you'll see this in the movie, but I'm just showing you what to look for. And then you'll see these, actually there's a pair of interfaces that if you look, and they'll gradually eat up the whole domain. This part, the darker part, is the austenite. Okay, so here's the movie. But it shows dramatically how important compatibility is in these. Eventually it sort of straightens up, so it's actually quite interesting. So why did that happen? So it waits until the and it turns out that geometrically you can't nucleate it either in the interior. Well, of course, the soldering iron is not touching the interior, but you can't nucleate it on the face, and you can't nucleate it on an edge, but you can nucleate it at a corner. So this calculation shows that. Okay, now there's another very interesting story about special compositions. And so this began with a student of Dick James Bhattacharya, who studied the wedge microstructure. So what it looks like, so it's austenite outside the wedge, and then there are two laminates of martensite, which on the one hand fit onto the austenite, and on the other hand fit onto each other. Okay? This is a very common thing to see. And it turns out that, remember, in cubic orthorhombic, there are three parameters, alpha, beta, and gamma. So it turns out that you can only make this configuration if alpha, beta, and gamma satisfy a relation, some algebraic relation between them. And it turns out that that relation holds high accuracy for the actual compositions of the, so I should say that, okay, so because these alloys are mixtures of different, here, copper, aluminum, and nickel, right? And so you can vary the composition, how much aluminum there is to copper, how much nickel there is. And when you change the composition, it changes the deformation point. So it changes the alpha, beta, and the gamma. Okay? So it turns out that the compositions which were used in shape memory alloys exactly allow this kind of microstructure. And then, remember I told you that to make an exact interface between austenite and martensite, you require the middle eigenvalue to be exactly 1. And I'm a mathematician, I thought, well, that's a very uninteresting situation, because it's never going to happen. But Dick James was an experimentalist, and he asked a much better question. He says, well, what's going to happen if we make an alloy that has a middle eigenvalue 1? And what's more, there are some other conditions called the cofactor conditions that allow you to make in a classical austenite martensite interface, the lambda, the volume fraction, anything you like between 0 and 1. And so when you construct an alloy like that, which is not a trivial thing to do, you have to vary the composition to make these deformation parameters do what you want. Then the hysteresis, the thermal hysteresis. So now you're cycling around the critical temperature. You're going from austenite to martensite, so you have to go below theta critical by 7 amount. On the other direction, you have to go above theta critical by a certain amount, and that difference is the hysteresis. In a typical shape memory alloy, it's about 50 to 70 degrees centigrade. With these alloys, it is 2 degrees centigrade. And the material is undamaged after thousands of thermal cycles, in fact, millions for materials that were later discovered. And furthermore, during the thermal cycling, remarkable microstructures appear that are completely different in every cycle. So I'll show you a movie of this. So there's the alloy, zinc, gold, copper. And we're cycling, but we're going to cycle it. That's austenite, martensite. Austenite, martensite. They're different every time. These pictures are different every time. So it shows it's an extremely unstable configuration, a sort of stochastic situation where some little thing that happens sends the microstructure off in a completely different direction. So there's all sorts of work on this. Well, I would say it was not actually understood, and potentially it can have very interesting technological applications. Here's another example now of a polycrystal which has middle eigenvalue 1. This is still unpublished micrograph of Minori in Amura. This is cubic to orthorhombic, and now you see we'll talk about polycrystals later, but here's a 1 grain polycrystal, and you see that well, it's very difficult to see what you see here, right? I mean, it's a very complicated configuration of gradients, and actually so it's cubic to orthorhombic, so there are 6 martensitic variants. Here's this one in the middle is supposed to be the austenite, and so if you do a calculation, you find that there are rank 1 connections. There are 2 rank 1 connections from the identity to each well. So there are 12 possible. So if you imagine you're going from, you're reducing the temperature, you're going from the austenite to the martensite, you might expect to see these 12 gradients that appear, right? Because they're the ones that you can make an exact interface with the martensite from. But the interesting thing is that none of those 12 matrices are rank 1 connected. So you can't make a rank 1 connection between any pair of them. So I believe that this is some kind of experimental approximation to an exact gradient that takes 12 values, none of which are rank 1 connected. So it's known that there are such, it is possible to construct such things. So also there's lots of things we don't understand.
The needles in there, are they actually parallel like they look?
Well, I mean, so yeah, so I mean, this is nucleated some. So presumably in this red thing here, the gradient is essentially constant, and then in say this one here. So the different colors are the amount of work that goes into this experiment is incredible. I mean, it was, you know, they do it and then they slice it and then they polish it and then they image it using polarized light. But I mean, more or less in each of these things you expect the deformation gradient to be constant. So it's as if sort of every interface is fractal. More or less this sort of. Okay, so there are more complex interfaces. So ones like that. And here I've drawn in yellow one there, one there. And then you require some analysis of more complicated situations other than the Hadamard jump prediction. And so with Carstensen, I have some results of that type, which tell you. So for example, if you have a Lipschitz map here and a normal and a point A here, then you can define dy plus of A, that's a set of matrices, which are sort of the limiting values as you approach this point from the positive side, and dy minus of A, similarly from the negative side. And they're related in this way that 0 has to belong to the quasi-convexification of dy plus of A times identity minus n tends to n. N is a normal and minus the same on the other side, all quasi-convexified. So various results this time. Okay, and another interesting model for trying to understand how you get from the austenite to the martensite. So, you know, you nucleate various bits of martensite, and then another bit nucleates, and then another bit, and eventually it's all martensite. So here's a very simple sort of probabilistic model that seems to capture something of what is going on. So let's take a square, and we're going to imagine that you're allowed to have interfaces which are horizontal and vertical only. So you take a point in the sphere, in the square at random, and with probability, let's say a half, you choose a vertical interface through there, and with probability a half, you choose a horizontal interface through there. So, okay, suppose it's horizontal, right? And now you do it again. You pick another point, and now you pick another, whether you go horizontally or vertically. Now when you go vertically, you're not allowed to go further than the first one, okay? And you continue like this. Another one, okay, and so on, right? So simulations show that you get, that's with 2 directions, with 4 directions, and this is not so different from the sort of pictures that you see, actually. And it's been put into a sort of generalized branching random walk analysis by Heriot-Watt and Ben Hamley. Ben Hamley is a probabilist in Knoxville. And it predicts sort of approximate power laws for plate lengths as are observed in acoustic emission experiments for these transformations done in Barcelona. Okay.
Images also there when one looks at tilings by long bars, big long bars and big tilings by the box, then you see some images.
Okay, let me tell me about those later. So finally, I want to say a little bit about polycrystals, because most alloys form polycrystals. So, so that means you have a different orientation of the crystal lattice in each grain. Okay, so when it crystallizes, it forms these grains, and in each grain you get a different orientation of the lattice, as indicated here. So, so this would be, say, a cubic austenite phase for temperatures bigger than them in critical temperature, it might look like this. And we're interested in what microstructure arises from a Martensitic phase transformation in which the lattice changes shape at theta critical. And of course, we've already studied this for a single crystal, but now we have other things that happen. So here's a picture of barium titanate. This is a cubic to tetragonal transformation. Here's a grain, right? And we see the sort of microstructure in a grain that we were sort of discussing before, but also you see that that microstructure propagates from one grain to another. So you have to apply compatibility not only inside each grain, but across grain boundaries. So this is a tricky thing to do, which we're trying to do. So there's no diffusion, of course, within the grains or of the grain boundaries. So there are a lot of studies of at higher temperatures of diffusing grain boundaries. This is a separate subject in itself. But here we're measuring evidence. There's a low enough temperature for the grain boundaries to be fixed. So you can decide how to describe this grain geometry. So we'll suppose that that you could write omega as a union of the closures of these disjoint grains. So each omega j will be a bounded Lipschitz domain. They're disjoint, and omega is the union of the closures of those domains. And the interior grains are ones for which their boundary is contained in the union of the other grain boundaries, and the others are boundary grains. So actually, if you think about it, these two okay, so A and B are no, hang on a second. I've run out of battery on my pointer. Okay, that's what's okay, so okay, so A and B are interior grains, but they do touch the boundary. No, but it's different kind of battery. Thank you. Yeah. Okay, it doesn't matter. Okay. Very good. So use my finger. Okay, so one thing you can do is a sort of kind of trivial piece of complex analysis that if each grain is convex, then every interior grain has to be a polyhedron. A convex polyhedron. Okay, an intersection of a finite number of half spaces. And then you can ask, what about the triple points? These are points that belong to 3 or more grain boundaries. And so in 2 dimensions, you can show that there are at most 2 into n-2 triple points. So capital N is the number of grains. That's more or less a piece of topology. And in general, well, we don't on open problems in this area, I think, but at least you know that the triple points are nowhere dense in the union of the other boundaries. So I mean, that's kind of having this kind of information, which is seemingly geometrically completely obvious, is useful because we would like to know that most boundary points are ones where there's just one other grain on the other side, because then you can apply things like the Hadamard jump condition or generalizations of it across that. But if for example, a set of positive measure of points were triple points, then there would be a much more complicated compatibility calculation. Okay, so now
can you go back 2 slides back? Actually, that's the so in here is, I guess, a different phase, and it do it in this way.
Same materials, same materials.
Now,
well, I wouldn't use that language. I mean, when you deform it, it will, when it changes shape, then you can talk about different Martensitic phases or something. Yeah.
Excuse me, I have a quick question here. Am I audible?
Yes, please. Okay, let me answer this question first and then come to the one on.
Okay, I'm sorry. Okay.
So the question is, so mathematically, I'm a little lost as I'm thinking of a big convex shape, and then we assume that each is convex, and then when you are seeing that it implies that each has to be a convex polyhedron. Is it just because if I have different convex shapes and they fit together, they have to be
separated? Right? If it's a simple piece of convex, of course, it only applies to the interior parts. So yeah, so there was a question online. Please ask.
So what is small n in this theorem?
That's the dimension, space dimension.
Okay. So small n equal to 2 is it a thin film or something? Is that what you're talking about?
Sorry,
if small n is equal to 2, are you talking about a thin film, or is that how I look at it?
I didn't understand what the word was.
Saying that if you're looking at 2 dimensions, is it like a single layer, or is this like a thin film?
A thin film, yes, a thin film, yes.
Okay.
Like a thin film. Yeah.
Okay.
Yeah. Okay. Okay. So now, what's the simplest thing that could happen? Could you have a constant deformation gradient in adjacent grain? So suppose we have a flat part of the grain boundary, right? And on one side, so here's grain 1, and we have the gradient being A, and on the other side, in grain 2, which has rotated crystal axes, we have another gradient B. Right? So in order for that to happen, well, we can assume that the grain 1 has unrotated axes. Okay? So in order for that to be a zero energy deformation, you need that A would be some rotation times some UI, which was one of the Martensitic variants, and on the other side, it's a rotation times UJR. So R gives you the rotation of the crystal axes in the second grain with respect to the first one. So R is given to you. Okay. Where Q1 and Q2 are in SO3, so R represents the rotation of grain 2. Well, we'll see that in general, that's not possible. It's not possible. And that's why we expect microstructure and grain boundaries, which is what we saw in the pictures actually. So, for a rank 1 connection, well, we know that this matrix has to have 0 determinant, right? That was the calculation. So I've got UJR, so I take that transpose times itself, I get R transposed UJ squared R. And so we know that this matrix has to have 0 determinant, and it has 0 trace. And so if it has 0 trace and has 0 determinant, then it has to be of the form lambda E1 plus E1 minus E3 times E3 with the eigenvectors. And you can write that in the form given in the theorem, right? So E1 plus E1 over root 2 times E1 minus E3 over root 2. That's the sort of transpose of that. So if the determinant E is 0, and then you know that you can. So it's necessary and sufficient. The determinant of E is 0. Okay. And the possible grain boundaries are given by E1 minus E2 over root 2. Now, if E is actually 0, then that means that the two energy wells are the same. And so we know that there are no rank 1 connections between the well and itself. So that means that the gradient won't jump. So there'll be no jump in the gradient. So that's not what we're interested in. So then the question is then, for what R is it possible for this determinant to be 0? So we're given what the UI and the UJ are. So for what R can this be 0? Well, you know that the UI is related to UJ, conjugate to UJ through some R bar, which is in the point group of the austenite. And so, in fact, this determinant, you can replace UI by this, and then you see that it's the determinant of UJ squared minus R tilde transpose UJ squared, the same J times R tilde, where R tilde is R bar. Okay, so now we're interested in what the R tilde are, which makes determinant of uj squared minus R tilde, uj squared R tilde equals 0. And so we'll do that. Well, we'll let uj have spectral decomposition with the lambdas and the ek hats, and we'll let R tilde have rotation axis, which is expressed in terms of the ek hats as some nk ek hat, and rotation angle theta. So any in 3 dimensions, anything in S of 3 is a rotation of a certain angle around an axis. So you can represent it in the axis angle form, and actually that's what it is. It's cos phi times the identity plus sine phi capital N. N is this matrix. So NP is N plus P plus 1 minus cos phi times N tensor N. So that's it. And so you work it out. You shove it into the determinant, and you find that in fact the determinant is equal to 4 rho. Rho is the product of the differences of the squares of the eigenvalues times n1, n2, n3. Those are components of the normal times sine phi into 1 minus cos phi. So you see that it's 0 if and only if either 2 lambda k's are equal, or some component of n is 0, or the angle is either 0 or pi. Now, what's kind of interesting about that? Go back to that. No. Let's go to the end. Sorry. How do we do that? Yeah, keep talking. I'm just. This is the last. This is the very last line of the last slide. In fact, I've already said the last line, but I wanted to add something verbally. Yeah, so what's interesting is that for a cubic tetragonal transformation, 2 of the lambdas are equal, right? So you can make these interfaces, but of course, if you take a curve, most grain lambda is curved, and so and then you won't have this holding. So this is a calculation which is just the beginning of trying to understand some of the compatibility issues at grain boundaries.
Are there any questions from the audience? I have a few during the talk.
Or online.
And are there any questions online? Please feel free to unmute yourself and.
Hi, Professor Bod. I'm Vivek. I have a question. Can you just repeat what was happening in that microstructure of Pulley crystal? I think this was unpublished work. And you were telling me that the austenite, there are, I just want to, could you just go back and explain that figure once more? This was a Pulley crystal in which there was some unpublished work, and you said there is no, I think there were 6 or 12 variants, if I'm not wrong.
Yes, okay.
And I think the Martensite variants are just not so. So you were saying that not this one. I think
Okay. Yeah. So the thing is.
Yeah, this one. Yeah, this one. Yeah.
So the thing is that there's 2. You take the identity. There are 2 matrices on each well, which is
okay.
Connected to the identity. But there are no rank 1 connections between those 12 matrices. That's the thing.
So these interfaces that you're seeing are highly stressed interfaces. Is it is there a transition layer within the Martensite variants that we are not seeing here, or is it?
I mean, it's almost 0 energy. But of course, there's going to be stresses somewhere, and there's going to be boundary layers and so on. But it's very close to 0 energy.
Okay. 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 Thank you.
Yeah, you want to.
I have a question. I'm actually in material science, not a math. And what do you think would happen if you took a cone, like your Shiner experiment?
Yes.
Took a cone with the fixed spinning angles. So here you have fixed angles that are crossing parallel.
Yes.
I just think.
The question that people usually ask, so let me ask it for you,
Sure.
is what happens if, for example, you took a ball? Okay, so then there aren't any corners for the for the thing to nucleate at. And now Shiner says that it's extremely difficult to make such a specimen. And anyway, he didn't have so much of the single crystals of the alloy just there. So these are practical things that don't face mathematicians, that do face people like you, material scientists doing experiments. So I don't know, but presumably it would be, you know, you'd have to reduce the temperature a lot more in order for it to increase the temperature much more in order for it to transform to the hysteresis. Now you were saying, what if it was not a rectangular parallel pipette, but some slab or something? A cone at a fixed angle. Yes. Well, again, it would not be able to. Well, okay. Now I forget. I mean, we showed that you couldn't nucleate it at the interfaces, but the interfaces were. I mean, this specimen, the interfaces were parallel to the crystal. I mean, the three edges of the parallel pipette were in cubic directions. Now I'm not sure whether if you cut a specimen which had a face at a different normal, which was not it's possible maybe you could nucleate it there. It's a question of so-called quasi-convexity of the boundary. So in quasi-convexity at the interior sort of tells you that the only gradients you can see in a stable configuration are ones at which that the energy is quasi-convex. Quasi-convexity of the boundary is a stronger condition, and it limits the gradients you can see in a minimizer on a boundary. And there's a similar thing for edges and for corners. Well, I don't know. I mean, there's a lot of calculations to check that it had to occur. I mean, you could see, in the picture you could see the microstructure that was used because it was a combination of an austenite martensite interface with a martensite martensite.
Are there other questions, either online or offline?
I think if I'm understanding what you're saying about the wells, we can't actually pin these. From a material science point of view.
You can't pin them.
You can't pin these structures. Like
Yeah. Well, yes. I mean, of course.
you get it sudden shift.
I mean, we're talking about situations where there are relatively few dislocations, which are not going to be. It's very mobile stuff. It's very mobile.
So what do you think governs the speed there?
Well, I mean, I'm not. First of all, I'm not an expert in that, but there's a lot of people who are experts in it. But you know, from a strictly mathematical point of view, I don't know a single set of equations which I know have solutions which describe the propagation of these interfaces. And on one of the very interesting sort of mathematical questions is, I mean, if you found such a set of PDE, I mean, there's some candidates for that with visco elasticity of great type, then here we're in a situation where the minimum is not attained, and at least according to this model, and you expect to get infinitely fine microstructures. So will the dynamics actually do that historically, or are there solutions to the dynamics which really get finer and finer as T goes to infinity? We don't know.
we can take other discussions offline. If you have a quick question. Okay. So let's thank Prof. John. We should